0.1 of a standard deviation. And then the average in groups 2 and 3 were slightly above 0. But none of these differences are statistically significant. These are just kind of, again, probably just due to sampling variation. So again, the t-tests here indicate that none of these differences were statistically significant. It looks like at baseline, if we look at sanitation, asset ownership, health, or education, the schools look really similar. So it's probably valid to compare them in terms of their later outcome when group 1 gets deworming. Let me pause for a second, see if there's any questions or any other patterns you see in the data here. Yeah. Yeah, so in some ways, this doesn't get at the omitted variable issue because they're omitted, we can't measure them. It's always going to be possible that there's some omitted variable that, just by chance, looks very different between the different groups of schools. By doing this, at least we know that along all these different dimensions we can measure, we have a ton more characteristics than this. I just pulled a few of them. Across dozens of characteristics, they look exactly the same. So it would have to be a really weird omitted variable that doesn't correlate with health, that doesn't correlate with education, it doesn't correlate with wealth, but somehow affects educational outcomes. So it starts feeling really implausible that there is such an omitted variable. The larger the sample, the more balance typically you have. Now, in some ways we have a really big sample. We have like over 30,000 kids, but we only have 75 schools. So let me just mention an issue. It's not going to really feature in the problem sets, but for people interested in this, there's always a big debate about the level of randomization that comes up. In general, it's very nice to have a very low level of randomization. By low level, I mean randomized at the person level. Because then within a given population, everybody has a different treatment status, and you should have less sampling variation because you have more of these draws into treatment and control, right? Imagine the following. Let's look at this classroom. There's 100 of you roughly in the classroom, but there are, let's say, 10 rows. I could either randomize each of the 100 people and have a sample size of 100, or I could randomize rows into treatment and control. Now, maybe randomizing rows is fine. Maybe the people sitting in each row are kind of representative of the whole population. You guys just happen to sit down somewhere. If it's really random who's sitting in which row, doesn't matter. I can randomize at the individual level or the row level. It's not going to really give me too much difference. But if for whatever reason the guys in the front row are just all really like hardcore, like you guys, I can see, I can tell, and the folks in the back are just like total slackers back there, just making it up. If that's true, and by chance the front row gets in group 1 and the back row gets in group 3, well then maybe that difference that I'm seeing between group 1 and group 3 is due to the fact that it just happens that people in different rows are really different. So it could be the same for these 75 schools. What if it's the case that there was 1 or 2 schools that were just like academically outstanding, much better than everybody else, and just by chance they all ended up in group 1? Then we'd be concerned that there's some kind of imbalance, right? Now it turns out there's really no baseline differences we can measure, so we don't think there were any strong outliers on those dimensions. Yeah. Yeah. Awesome. People, and this comes up, so when people have a limited sample size, sometimes due to sampling variation, 1 or 2 key characteristics look imbalanced. And the standard approach in this kind of statistical work or econometric work is then whenever you run your regressions, you always control for that variable. So if you find characteristics that look really imbalanced, you always put those on the right-hand side as a control, because clearly there was some imbalance due to sampling variation. If you don't find any visible imbalance, then you don't even need to control for anything. You can just take the average difference across the groups. That's what I'm going to do here today. But that's the answer. So if you only have a sample of 50 or 40 or 60 or even 100, and by chance you have imbalance, you control for the variables that look imbalanced. Yeah. When we started, we were interested in both. It's funny you asked that question. Just yesterday, I went back to look at our original funding proposals from 1997 and 1998, and for another reason. And the 2 educational outcomes we were really focused on were basically like school attendance. There were 3. It was school attendance, school dropout, and test scores. So I think up front we were kind of equally interested in both. Now it's going to turn out we had big effects on one but not the other. And that's interesting, I think, on its own. But going in, it wasn't like we necessarily thought one was more important than the other. And certainly in the case of African schooling, as you've seen, a lot of settings, a lot of countries have low enrollment. So just keeping kids in school and getting them in school is very important. It isn't like that problem's been solved. Do you have a follow-up on that? Yeah. Okay, so this was an issue, which was the only attendance data that we had was from school registers. So we actually had one observation from we took school registers before the program started, and we took sort of attendance. Now, in the education literature, there was already at that point conventional wisdom that official school registers aren't that reliable. That teachers are sometimes like a little bit lazy about just checking present. And the way we collected attendance, and I'll talk more about this in a few slides, is we didn't use registers. We sent our teams of enumerators to schools on unannounced days. We're like, we need to measure attendance better. If we care about this, we have to measure better. So we came up with a schedule in the office week to week, and then told the team in the morning, okay, you're going to this school today, go and collect attendance at that school. And they would show up. All the school headmasters knew this was going to be the plan. We were told we are going to visit on unannounced days, and on those days, just let our enumerators go and check who's in class, who's present. When we do that, we find much lower attendance rates at these unannounced checks than in the school registers. So we don't feel like the registers are that reliable. Now, maybe they're not as bad as we thought. At baseline, we do have that one attendance check, and it looks balanced across the 3 groups. So there was no kind of strong evidence of difference. We just don't put much weight on that evidence. Was there another hand up? Yeah. Radhika. Yep. Yeah, we have data on that, and I probably won't get to it today, but I'll get to it on Thursday. And that was balanced at baseline, and I'll show you what the program did to that variable, because we collected that over time. So for instance, I mentioned last time that in addition to the drugs, there was also health education, saying like, don't play Lake Victoria, you're going to get schistosomiasis. So I'll show you the effect of the program on that, on how kids answer that question. But I think that'll be Thursday. Yeah. What does it mean to control for it? Yeah, so let me go back to the equation here. Here, I'm imagining that these x's are unobserved, right? So we really only have treatment and then the y variable. But in reality, there could be a whole series of other variables included as controls here that we can call z, let's say. So let's just, let's call this the coefficient. And let's say there's just some vector z of characteristics that we can observe. So let's say in that vector z, we include all the variables that look imbalanced at baseline. So just in a multiple regression, you're not only worried about the correlation between these 2 variables, you're interested in the partial correlation conditional on everything else you can control for. And that's really what a regression is giving you. So what we're saying is, yeah, maybe there is some imbalance on z. We're going to include that in the regression, basically difference that out, and focus on the residual partial variation between y and t. Does that make sense? Okay. Great. Okay, so we went through these. So let's go through and show you some results. So the next thing we did, we had baseline, the drugs were administered, the health education took place, and then we went back and did follow-up surveys. I already mentioned that we did these regular follow-ups of school attendance. At the end of each year, there was an exam, academic exam that was administered. We also, 1 year later, collected data on health, and we measured health using the actual worm infection status, where we had to collect stool samples, again, and count out the number of worm eggs in the stool samples. So those counts tell us how sick the kids are. They tell us basically how many worms are in their intestines. This is almost like like the first step. I mean, if the deworming drugs in the program didn't even reduce worm infection, then there's kind of nothing we'd expect to see on anything else in terms of education or any other gain. So the first thing we do is say, is there a gain in terms of reducing serious worm infections? And so basically, we're interested to start in this difference. The average here, the y, is going to be having a serious worm infection between the treatment group and the control group. Now, we did this by comparing group 1 minus group 2, and we collected this data in early 1999. Now, let me explain why we did that. First thing you would say is, why didn't we collect group 1 versus groups 2 and 3 together? The reason why is we only collected health data, that very detailed sort of stool samples and peristological data on group 2 in early 1999. And we did that because when we were setting up the project and working with the Ministry of Health, there was a feeling that we could only ethically collect health data on people who were going to receive treatment. So at baseline in 1998, we only collected the worm infection rates for group 1. We collected in early 1998, and a month later they got treatment. So there was no sort of issue there. In early 1999, group 1 has been treated. Group 1 got treated in 1998. There were 2 rounds of treatment, actually, every 6 months. In early 1999, we collected the next round of this health data, these stool samples, just before group 2 was going to get treated. So group 1 has been treated, group 2 has not yet been treated. We have treatment versus control, but there's no ethical issue because we collected data on group 2, and a few weeks later they get treated too. So the downside to this is we don't have data at baseline showing that actually worm infection rates are balanced across groups 1, 2, and 3. Independent of the ethical issues, of course, we would have wanted that data to show there was this balance. Now, we did show there was balance on a million other things, but we didn't show it on that dimension. So that's one limitation of the data, and it's just an example that when you do research, of course, you're not fully unconstrained. You can't just get the data that's good for your statistical approach. There's ethical constraints, institutional constraints, logistical constraints, financial constraints in terms of how much data you can collect, and you have to kind of optimize your data collection in that world that you're in. So what do we find? When we compare rates of moderate to heavy worm infections in 1999, early 1999, we find the average rate in group 1 is 27%, and the average rate in group 2 is 52%. So there's a drop of half in moderate to heavy worm infections. So half the kids in group 2 had a pretty serious infection. Remember I told you last time that there are different standards for what constitutes a serious infection by worm, and you can count the eggs and stool samples. So half the kids in group 2 had those, and about a quarter in group 1. And that difference is statistically significant at 99% confidence. Very significant difference. So there's a big reduction. But let me ask you a question. Why was the infection rate in group 1 not 0? How didn't they just receive treatment? What are the reasons why it wasn't 0? There's at least 3 or 4 reasons you can think of. So maybe, yeah, in the back. Yeah, so you're saying maybe there's reinfection. Maybe group 1 has some infection. Yeah, we treated them. Oh, I should mention the timing. So there was a round of treatment in early 98. There was a round of deworming treatment in like October of 98. And then these data were collected in like February or March of 99, just before group 2 got treated. So this is 6 months after group 1 had received treatment. So you're making an excellent point, and that's one of my kind of core explanations, is group 1 could have gotten reinfected. So yeah, you cleared the worms, but since they're still surrounded by all these other schools that have tons of worm infections, they're getting reinfected. So that's one plausible explanation. What's another one? So that's another core point. Take-up of the treatment was about 75%. There were a few percent of kids who didn't want to take it on the day of. They refused. There were a few percent of kids whose parents didn't want them to take it. But the bulk of the explanation for why it wasn't 100% treatment was what you said. Some kids were absent on the day. The public health nurse came with the drugs. So they missed treatment. So about 75% treatment rate. So some of this infection is just due to the fact that not everybody got the drugs. Okay, that was 2. Can you think of a third explanation for why it's not perfect? Potentially, yeah. Okay, so you're raising the issue that maybe some of the kids in group 1 had been in another school the year before and hadn't gotten treatment. Now, I should have said, I forgot to mention that when we're classifying people here in all the analysis I'll show you, like group 1, group 2, and group 3, I'm going to define them that way based on the school they were in at the beginning of 1998. So even if you switch school from the point of view of our analysis, you're always group 1 or group 2 or group 3. So your explanation could still be right in the sense that if I was a group 1 kid who early in 1998 potentially switched to another school, then maybe I'm infected because I never got the treatment in my assigned school, and then it could go the other way in group 2. So you're raising an issue that could be important here, these transfers. Yeah. Yeah, that's right. So even beyond the point of maybe there's a spread across these different areas, people can get infected very close to home, and if their behaviors don't change, they're going to get rapidly reinfected. So it's slightly different than but related to the point before about reinfection being a possibility. Okay. The last sort of explanation, so you guys have raised lots of really good points. Why not 0% in the treated group? You guys have kind of nailed all these points, except for point 2, which is only 75% compliance with assigned treatment. So that's pretty good. Most people took it, but not everybody. 2, the drugs are thought to be very effective, but they're not necessarily going to be perfect for every individual. There's some variation in every person's reaction to a drug. So maybe for some people, yes, the worms killed, all the worms were killed, and for other people, maybe they only killed some of the worms. So that's possible. And then there was this point about reinfection because we're measuring infection 6 months later. So for all those reasons, you might see these differences. And there was a point about the transfers across schools, which could be potentially important. Okay. Yeah. Yep. No, randomization does. The estimates I'm showing you here should be unbiased. There was the randomization on everything we can measure. The schools look totally balanced. There's no reason to think there's any imbalance in infection rates across groups 1, 2, and 3. So the randomization should account for, in theory, with randomization, you don't even need baseline data. You can randomize. If you have a large sample, you randomize. You can just get one follow-up survey round and compare differences, and that's fully valid data. Exactly. You can only get stool samples from groups that were going to get phased into treatment soon. Yeah, the people who I think judge the paper don't think it's that big a deal. In a perfect world, I'd love to have the baseline data showing they were exactly the same at baseline, because it would rule out any doubts people could have that there was some weird sampling variation. But there's no reason to expect the sampling variation because of the randomization. So there's no reason to systematically think it's biased. It might just be bad luck that there's some sampling variation. But I think the fact that we show so much balance along all these other characteristics makes it feel like it's highly unlikely that there was a lot of imbalance in that characteristic. Yeah.
How did the infection rate of group 1 and when you took the sample in 1998, how did that compare to the 50% of group 2?
That's a great question. So let me mention that now. Group 1 in 1998 had somewhat lower infection. Group 1 in 1998 had 37%, not 52%. So this kind of gets into this issue. Oh, maybe there were some differences. There was something very important that happened in 1998 that affected the local health environment a lot. And I was in the field for this, and it was a very important event, which was 1998 was an El Nino year. And there was widespread flooding in all of western Kenya near the lake. There were cholera outbreaks. Schistosomiasis infections with that kind of flooding of the lake almost certainly go up. A lot of latrines, because the water level was so high and there was so much water, a lot of latrines flooded, which would increase the risk of geohelminth infection. So it's not at all surprising, I think, from an epidemiological point of view, that you would have somewhat higher infection in 1999 than in 1998 because of all the flooding. So I think that's the best explanation for the difference between 98 and 99. But again, the fact that they do look different across years raises this possibility that somehow maybe there were some baseline differences, which we don't have data on, so we can't directly test for that. Yeah. One thing I can say is when group 3 got phased in 2 years later, in a non-flooding year, a non-El Nino year, the average infection rates in group 3 looked a lot like group 1 in 1998, before the sort of El Nino flooding. Now, that isn't proof necessarily of anything, but it's consistent with the story that there was some sort of spike in infection in 98 to 99 because of all the flooding in 1998. Now, this raises an important issue of external validity. We're estimating in 1998 the treatment effect in a year where there were probably lots of worms. This was already an area with lots of worms. And then with all the flooding, there were even more worms. So we're kind of measuring the effect in an area with lots of serious worm infections. Like in group 2, it's 50% of serious worm infections. So there is the external validity issue. Maybe the treatment effects in a place that would only have a 30% or 20% or 10% serious worm infection burden, maybe those treatment effects would be smaller, presumably, because there was less disease. And I think that's a reasonable interpretation of the results. On the other hand, the fact that infection rates were so high in almost the whole population, from an analytical point of view, is sort of useful because it gets us closer to estimating the effect on a seriously infected person. So if we're interested in that effect, sort of at a personal level, these results are closer to that treatment effect of treating an individual who's seriously infected, probably. Yes? Some of the variables are a complete survey. Some of the variables are random sample. So for instance, the school attendance checks were the full sample. A lot of the surveys were the full sample of kids, at least in grade 3. Some of the younger kids were harder to do the full survey on. The peristological sample was a representative subsample, a random subsample of kids in that grade. So we don't have data on the full sample for these stool samples just because it's so expensive. Basically, the logistics of getting the stool samples and testing them took so much time and money that we can only do it for, how many kids was it? 30 kids per school? Between 30 and 45 kids per school. I'm forgetting the exact numbers. So we had the stool samples for a couple thousand kids. We have the attendance data for like 30,000 kids, something like that. Yeah.
So you said the drugs are not perfect?
Yeah.
You think the kids treatment for about 40 or 20% of the
Yep. Yep. Did the drugs change or? No, it was exactly the same drugs over time. And those are still the standard drugs even now. They haven't changed. The recommended WHO recommendation is still the same. Yeah. A couple years later. Yeah, in 2001 when group 3 is surveyed, which was not an El Nino year, their baseline infection rates look more similar to group 1 rather than being as high as group 2. This is one way to think about an experiment. If we really divide the groups into truly comparable groups, then in the absence of the treatment, we would expect group 1 and group 2 to have very similar time patterns. There's no reason why over time the variation wouldn't be very similar. So you can think of group 2 as a sort of counterfactual, that in the absence of all this treatment, the infection rates in group 1 would have been higher. But because they were getting the treatment, it was a lot lower. So another reason here why we still have like a quarter of the kids with serious infections in group 1 could be the case that this was just a really bad disease year. There was just a lot of reinfection this year. And that's the reason why infection rates are quite high, even after getting the drugs. Does that make sense? I think the variation over time is something that people, I think when they're first grappling with an experiment or the implications, it's a little bit of a different concept. It's very easy to see when you initially randomize that people should be kind of similar today. But imagine there's some time pattern of variables. There's also no reason why over time those groups would diverge. They were just randomly chosen. So there's no reason why groups 1 and 2 would look different in 99 other than the treatment. So that's the idea. Okay, what else looks different? When we ask the kids if they've been sick in the last week, you'll notice two things here. First, there's fewer kids saying they're sick in the last week in group 1. So self-reported health improves. But the general disease environment's pretty bad in 1999. 40% of the kids are saying they were sick in the last week. Some of them were saying they didn't feel well, they were low energy. Some of them were saying they had fever. With all this flooding, there was a lot of infectious disease. As I mentioned, including there was a cholera outbreak in parts of the study area. So there was a lot of disease, but kids are looking healthier in group 1. In terms of nutritional measures, and these are normalized in the same way. The Z-score means normalized, mean 0, standard deviation 1. There's also a slight increase in height in the group 1 schools between 98 and 99. And again, if you're healthier and you don't have all these worms in your intestines, you should have slightly better nutritional status. So this is consistent with that view. These aren't huge effects though. This is around 0.1 of a standard deviation, but it's kind of going in that same direction of kids being somewhat healthier. And then we also collected data on hemoglobin. So hemoglobin relates to anemia. So if you have very low hemoglobin means you have anemia. Sorry, let me use the eraser. Okay, so this is another point to raise. Hold on. So anemia.